In 1945, the science fiction writer Arthur C. Clarke first explored the idea that satellites could be used for broadcasting. Using Kepler's laws of planetary motion and Newtonian mechanics, Clarke's paper gave the exact conditions for putting a satellite into geostationary orbit. Today, there are hundreds of such satellites orbiting the Earth, and SES Global's operating companies and partner companies around the world operate over 40 of them. They provide audiovisual entertainment and information, broadband data and telecommunications services to an area that is home to 95% of the world's population. So how does the geostationary orbit work? A body of any sort orbiting the Earth, one such as our Moon, for example, stays in permanent orbit when the gravitational forces attracting it to the planet are balanced by the centrifugal forces generated by its speed of travel around the Earth that tend to send it flying outwards. The speed at which a satellite needs to travel for these forces to be in balance depends on its distance from the planet. Near the Earth, where the gravitational attraction is greater, its speed would have to be very high, and anyone wanting to receive signals from the satellite might only be able to do so for a couple of minutes at a time. In the same orbit as our Moon, they'd be able to see the satellite for about 10 hours a day, but in either case, they would need a reception dish which constantly tracked the moving satellite across the sky. But at 36,000 kilometers above the equator, about 1/10 of the way to the Moon, and with a speed of 13,000 kilometers an hour, a satellite will stay in orbit at the same point or orbital position over the Earth as it rotates. And that means that viewers on the ground can pick up signals 24 hours a day, 365 days a year, from a fixed reception dish. An orbital position is actually a box, about 150 kilometers each side, in which the satellites are parked. In addition to the major forces that keep the satellites in orbit, they're subject to other forces too. They're affected by the gravitational pull of the Moon and the planets, and by distortions in the Earth's gravitational field. Mountain ranges, such as the Himalayas, can pull them off course. On the ground, at control centers located around the world, huge parabolic antennae track each spacecraft. The control centers receive a constant flow of information from each satellite, telling them their precise locations at all times and the exact status of the onboard systems, which are exposed to the harsh environment of space. Highly skilled engineers control their fleets in space, monitoring flight dynamics and carrying out precision maneuvers. By remote control, the onboard thrusters are fired from time to time to ensure that the satellites remain in their geostationary positions, thus maintaining the highest quality of program transmission 24 hours a day, 365 days a year. Satellite operations become even more complex and challenging where several satellites are co-located at the same orbital position. This is the case in Europe, for instance, at SES Astra's orbital positions of 19.2 and 28.2 degrees east. The co-located satellites are constantly monitored and controlled to synchronize their flight from the Astra Satellite Control Center at Château de Betzdorf in Luxembourg. Co-locating satellites means that Astra can supply many more channels and services from an orbital position than could ever be carried on a single satellite. It also means that the system has built-in backup and reserve capacity should one satellite or part of a satellite fail. The lifetime of a satellite in space is mainly determined by the amount of fuel it carries for these station-keeping maneuvers. And the SES Global companies around the world have an outstanding track record of successful satellite management. Through careful planning and efficient use of that fuel, the engineers maximize the lifetime of our satellites, while at the same time guaranteeing an unrivaled 99.99% network availability for our clients.